Today we are going to talk about probability, and the concept of probability is central to the science of statistics. This is one of the fundamental concepts and central concepts on which statistics, and in particular the inferential statistics, is based. So this is a basic and central topic to cover in statistics, especially in inferential statistics. Now, what is meant by probability? What is the meaning of probability? The word probability is related to the words like probably, likely, or chance of something. That when we are talking about chance of something to occur, when we talk about likelihood of something to occur, that this is something which is likely to occur, this is something which has a chance to occur. And when we say that this is going to probably happen or this is probably not going to happen, so we are basically talking about the probability of that something, probability of that outcome to occur. So this is the meaning of probability that we use in our daily life whenever we are talking about likelihood of something or the chance of something. For example, when we see dark clouds on the sky, so what we are going to say is it is probably going to rain, right? So we are talking about the probability of rain, that it is probably going to rain. Or we say it is likely going to rain, so it means that we are again talking about probability that it is likely to rain. Or we can say that there is a good chance of rain. So this is the thing that we use in our daily life as well. When we talk about chance of something, when we talk about the likelihood of something, and when we talk about probability of something. So this is basically probability. And this is the concept of probability that we have in our daily life. So what is the meaning of probability? Mathematical theory of probability arose from the study of games of chance. And you know what are the games of chance? So the mathematical theory of probability arose from these games of chance. So probability is basically quantifying the chance with which the stated or nominated outcome of an event will take place. So this is the meaning of probability in statistics or in mathematics, right? That what is probability? Probability is quantifying the chance with which the stated or nominated outcome of an event will take place. So what is the meaning of probability in literal meaning? In literal meaning, probability means chances or likelihood of anything. So in statistics, it is basically the measure of likelihood of an event. So probability is quantifying the chance that you are giving the chance in numbers, right? So you are giving the chance in a number on a scale by which the stated or nominated outcome of an event will take place. And when we say quantifying the chance, it means that we are going to give a number of the probability, and by convention, the probability values, they lie on a scale between 0 and 1. And 0 refers to impossibility, and 1 refers to certainty. So the value of probability, that when we quantify the chances of an outcome, right? So that quantification, that value lies between 0 and 1. And when the value is exactly 0, it means that that event is impossible to occur. That outcome is impossible to occur. And when we have the value of 1 exactly, it means that that outcome is definitely going to, that outcome is certainly going to occur, right? And in terms of percentages, we can say that there is 0% chance of something, and 1 refers to 100% chance of something. So the probability value usually lies between these two values. The closer it is to 0, the less chances, the less likelihood it has. The closer it is to 1, it has more chances, more likelihood to occur. So this is the meaning of probability in statistics, that probability simply means taking the chances or the chances of something, right? So in mathematics and statistics, probability means to quantify those chances, right? And this is the measure of likelihood of an event, and the value lies between 0 and 1. Now, when we say that probability is basically quantifying the chance of something to occur, and we have to calculate the value of probability. So how we are going to do that, how we are going to calculate the probability value. So this is a simple formula. It is a number of nominated outcomes divided by the total number of possible outcomes. So this is the simplest formula of calculating probability, that we are actually quantifying the chance of something to occur. So we have to take all of the outcomes, the number of all of the possible outcomes, and then we are going to divide the number of nominated outcomes by that total number of possible outcomes. And that is going to give us the probability of that nominated outcome. So nominated outcome is that something which we have nominated and for which we want to calculate the probability. And the possible outcomes is all the other outcomes, right? The total of all the possible outcomes of that event. And we are going to take the simplest example for this. So coin tossing is the best example to describe the basics of probability calculation. So we have an event which is coin tossing, that we are going to toss the coin, right? Like we do before our cricket match starts. Outcomes are head and tail, right? So the outcomes could be head or a tail because it has two sides, the head side and the tail side. And for example, if we have chosen head, so our nominated outcome in this case is head. And how many times head is present in a single coin? So in a single coin, there is only one head which is present. So what is the total number of the nominated outcomes in this case? The total number of the nominated outcomes is 1. So our nominated outcome is head. And how many times this head is present? This head is present only once. So the number of nominated outcomes is 1. And what is the total number of possible outcomes? Because we have 2 possible outcomes, so therefore this number is going to be 2. So head is present only once and tail is present only once as well. So we have 1 plus 1, which is equal to 2, right? So now we have 2 possible outcomes and our nominated outcome is 1. So what we are going to do is we are going to divide the nominated outcome number by the total number of possible outcomes. So we are going to divide 1 by 2 and it is going to result in the value of 0.5. So this is the value of probability that we have calculated, and this is 0.5. And you can see that it is exactly in the middle of the scale. So it is in the middle of 0 and 1, and this is 0.5. And how much percent it is? It is 50%, right? So what we are going to say is that probability of head in a single event of coin tossing is 0.5, right? So the probability of head in a single event of coin tossing is 0.5. So this is how we have calculated the probability of head to occur when we have an event of coin tossing. So when we have an event of coin tossing and our nominated outcome is tail in this case, right? So we are taking tail as our nominated outcome. And how many times tail is present? Tail is present only once. So the nominated outcome is 1. And what is the total number of possible outcomes? It is 2, head and tail. So we are going to calculate the probability by dividing the number of the nominated outcome by the total number of possible outcomes. So we are going to get 0.5 value. So again, we are going to say that probability of tail in a single event of coin tossing is 0.5, right? So this is the meaning of probability, that we have to count the number of nominated outcomes, right? And then we have to divide that number by the total number of possible outcomes. And by dividing this, we are going to have the value of probability, and this value should lie on a scale between 0 and 1, right? And now we are going to take another example, which is the dice, and how many faces there are on the dice, how many sides it has. So it has 1 to 6 numbers on 6 sides. So this is basically a dice. So our event that we are talking about is dice rolling. And the outcomes are 1, 2, 3, 4, 5, or 6 because it has 2 sides, 6 sides. And nominated outcome is, for example, 6, that we want to calculate the probability of 6 in a single event of dice rolling, right? So what we are going to calculate is we are going to calculate the possibility or probability of 6 to occur in a single event of dice rolling. So our event is dice rolling and our nominated outcome is 6. Now we have to find out that what is the number of 6, that how many times 6 is present. So 6 is present only once on the dice, so therefore the number of 6 is only 1. And what is the total number of possible outcomes? All of these numbers, 1, 2, 3, 4, 5, 6, they are present only once. So each one has a 1 number. So this is going to sum up as 6. So the total number of possible outcomes is 6. And now calculate the probability. So probability is going to be 1 by 6. So 1 is the number of our nominated outcome and 6 is the total number of possible outcomes. So this is going to be 1 by 6 and it is equal to 0.1667, or in terms of percentage it is 16.67%. So we are going to say that probability of 6 in a single event of dice rolling is 0.1667. And again, you can see that this value lies on the scale between 0 and 1, right? And for example, if our nominated outcome is 3 this time, that we want to calculate the probability of 3. So how many times 3 is present? 3 is present only once. So the number of possible and number of nominated outcome is 1. And what is the total number of possible outcomes? It is 6. So we are going to calculate the probability of 3 to occur in a single event of dice rolling. And this is going to be 1 by 6. And this is 0.1667 or 16.67%. So probability of 3 in a single event of dice rolling is 0.1667. So this is how we calculate probabilities. Now these examples of coin and dice, so these are the examples which are related somehow, and these are the simplest example because these are the examples in which all the possible outcomes, they had equal chances or likelihoods to occur. Like when we talked about the coin, right? So the coin has two sides, head and tail, and head is present only once and the tail is present only once. So each one of these two has got an equal chance to occur. And similarly, in case of dice, we have 6 sides and each side is represented by a different number from 1 to 6. And because each number is present only once, so each number has an equal chance to occur out of the total chances, which are 6. So these are the examples in which all the outcomes, right, all the possible outcomes, they had equal chances of occurring because they were equally present within the event. So these are the simplest examples of probability. And now we are going to see the more complicated example in which all the outcomes, they don't have an equal chance to occur. So here we are going to take another example in which all the possible outcomes, they don't have equal chances of occurring. Like in the previous examples, all the possible outcomes, they had equal chance of occurring. But now we are going to take an example in which all the possible outcomes, they don't have equal chances of occurrence. So we are going to take the example of a jar in which there is a collection of jelly beans, right? So there are jelly beans of different colors in this jar, and 10 of these jelly beans are red in color, 9 are yellow in color, 3 are blue in color, and 14 are pink in color. So each of these different colors of the jelly beans, they are present in different numbers within this collection of jelly beans. So if there is an event of picking up one jelly bean from the jar, right? So if you are randomly going to pick one jelly bean from the jar, and we are interested in finding out the color, for example, the red color or yellow color, blue color or pink color. right? So when we're going to pick up one jelly bean from the jar, the outcome could be the color. Either it could be red, it could be yellow, it could be blue, or it could be pink, right? So it could be of any color. And we want to calculate their probabilities. For example, we want to calculate the probability of the red jelly beans, that if we are picking up one jelly bean randomly from the jar, so what is the probability that that jelly bean is going to be of red color, right? So for that purpose, we have to apply the formula of probability. And for that purpose, we need to have the total number of the nominated outcomes and the total number of possible outcomes. So how many times red is present? Red is present 10 times in this collection, right? So the nominated outcome, the number of this nominated outcome is 10. And then the total number of possible outcomes. So when we take their sum, that how many jelly beans are there? There are 10 red plus 9 yellow plus 3 blue plus 14 pink. So we have total 36 possible outcomes, right? So what is the number of the nominated outcome? It is how many times that nominated outcome is present. It is present 10 times. And what are the total number of possible outcomes? It is 36, right? So probability is going to be 10 divided by 36. And this is equal to 0.2778 or 27.78%. So we can say that probability of picking up a red jelly bean in a single event is 0.2778. So this is our answer, that this is the probability of picking up a red jelly bean. Now you might have a question that if there are 4 beans, so why don't we calculate the probability by taking 1 by 4 for each of the beans, right? So this is quite a genuine question, that if there are 4 colors of the jelly beans in the jar and we're going to randomly pick up one jelly bean from there, so we should calculate the probability by taking 1 by 4 for that specific, for that nominated color of the jelly bean, because there are 4. But why we are not taking 1 out of 4 is because these jelly beans, they are present in different numbers, right? So you can see that the pink jelly beans, it is present in the highest numbers. So if it is present in the highest numbers, it has more probability of being picked up, right? And the blue jelly bean, it has it is present only 3 times, so its chances are not equal to that of pink because it is less in number. It is represented less in it. For example, when you talk about your class, so your class is dominated by the number of girls. So there are more girls than boys in your class. So if you are going to randomly nominate one of your class fellows to talk about probability, so what is the chance that this is going to be a girl, or what is the chance this is going to be a boy? So obviously the chances for a girl would be higher because the girls are present in higher numbers. So same is the case here, that although there are 4 colors, but these 4 colors, they're not equally present, rather they are present in different numbers. So each has a different probability of being picked up, right? So the probability for red to be picked up is 0.2778, right? We calculate the probability for yellow. So if our nominated outcome is yellow, so how many times yellow is present? It is present 9 out of 36, right? So yellow is 9 out of 36, so its probability is going to be 0.25, right? Or 25%. So probability of picking up a yellow jelly bean in a single event is 0.25. And now we calculate for the blue. So how many times blue is present? It is present 3 times, right? Out of 36. So out of 36 jelly beans, 3 are blue. So what is the probability that if we pick up a random jelly bean from the jar, we are going to pick up a blue? The probability is 3 by 36, which is 0.0833 or 8.33%. So probability of picking up a blue jelly bean in a single event is 0.0833. which is close to 0, right? And if you want to calculate the probability for pink, so how many times pink is present? It is present 14 times out of 36. So this is going to be 0.3889 or 38.89%. So probability of picking up a pink jelly bean in a single event is 0.3889, right? So this is the example in which all the possible outcomes, they don't have equal chances of occurring, rather each has a different chance, each has a different probability, and this probability is based on their occurrence. It is based on their frequency in the total number of possible outcomes, right? So this is one example. Now we are going to take another example, and this time we are going to take example from the field biology, and we are talking about a pond which is inhabited by only 2 species of Meniscus midge. So these are small flies, and we are talking about 2 of these species, Dixella automalis and Dixella attica. And this is the life cycle for these flies. This is the general life cycle of Meniscus midge. And you can see that A in this figure refers to the fly, and its larval and pupal stages, they are in the water, right? So therefore we are talking about the pond, that the pond is inhabited by 2 species of Meniscus midge, Dixella automalis and Dixella attica. And at what stage of their life they are going to be aquatic? They are aquatic during their larval and pupal stage, because when they become adults, they are flies and they are going to be outside of the water. Now the pupae of these 2 species, Dixella automalis and Dixella attica, they are morphologically similar, right? So when we look at their pupa, they are morphologically similar, and they are randomly and independently dispersed in pond. So if you look at a random pupa collected from the pond, you are unable to describe the species of this pupa, that which species this belongs to, because their pupae, they are morphologically similar. So you cannot differentiate, or you cannot identify the species unless the fly emerges out of that pupa, right? So you are going to only identify its species when the fly emerges out of the pupa, because their pupae are morphologically similar, right? So this is the example, and I'm going to repeat it, that we're talking about an insect species, a flying insect species of Meniscus midge, and this insect has got its larval and pupal stage in the water, and its adult stage is flying, right? So we are talking about a pond, and this pond is inhabited by 2 species of the Meniscus midge, Dixella automalis and Dixella attica. And these 2 species, they are closely related to each other, as you can see that they belong to the same genus, and their pupae are morphologically similar, and they are randomly and independently dispersed in pond, right? So unless and until you can see the fly emerging out of the pupa, you cannot identify which species this pupa belongs to, because the pupae, they are morphologically similar, so you cannot distinguish the species at that stage unless the fly emerges out of the pupa, right? So this is the example that we are going to take. So now that we have discussed that their pupae are morphologically similar of these 2 species of the Meniscus midge, so if we have randomly collected a pupa from the pond, then what this pupa is going to be? It is going to emerge as Dixella automalis, or is it going to emerge as Dixella attica? So if we don't have any previous information, then we will suppose that both have equal chances, right? So this pupa could emerge as Dixella automalis, or this could emerge as Dixella attica, because we don't have any previous information, so we are supposing that their probability is going to be 0.5 and 0.5. So they're going to have equal chances. But if we have a previous information, then we are going to calculate the probability according to that previous information that we have. So the long-term studies revealed that out of every 100 pupae collected from that pond, 80 will emerge as Dixella automalis and 20 will emerge as Dixella attica. So now we have a previous information about their relative distribution, that if we have 100 pupae, then 80 are going to emerge as Dixella automalis and 20 are going to emerge as Dixella attica. So in this case, we are not going to count their equal chances or equal probabilities. Rather, we are going to calculate their relative specific probabilities. And also about their sex, that the male to female ratio is 1:1, right? So we have information about this thing as well, that the male to female ratio is 1:1. So out of every 2 pupae collected, 1 will emerge as male and 1 is likely to emerge as female, right? So this is the information that we have, that if we have 100 pupae, then 80 are expected to emerge as Dixella automalis and 20 are expected to emerge as Dixella attica. And if we want to know about the sex, irrespective of their species, then out of every 2 pupae, 1 is going to emerge as male and 1 is going to emerge as female, right? So when we have a pupa randomly collected, it could be either Dixella automalis or Dixella attica, or it could be male or female. And now we want to calculate their probabilities, right? Their probability values. So we are talking about an event, and the event is hatching of 1 pupa collected from the pond, right? So we have collected 1 pupa from the pond, and the event is hatching of 1 pupa collected from the pond. The outcomes are Dixella automalis and Dixella attica. So these are the 2 possible outcomes, that it could be either Dixella automalis or it could be either Dixella attica. Nominated outcome, for example, is Dixella automalis, that we want to calculate the probability that what is the probability this pupa is going to emerge as Dixella automalis. And we know from the previous information that if we have 100 pupae, then 80 of them are expected to emerge as Dixella automalis. So the nominated outcome is 80, and the total number of possible outcomes are 100. So probability is going to be 80 by 100, which is 0.8. So probability of a pupa to emerge as Dixella automalis is 0.8. And likewise, if we nominate Dixella attica, so how many times it is present out of 100? It is present 20 times. And what is the total number of possible outcomes? It is 100. So this is going to be 20 by 100, which is 0.2. So probability of a pupa to emerge as Dixella attica is 0.2. So this is the probability for Dixella attica. If we want to calculate the probability for the sex, for the male and female probabilities, so the nominated outcome, for example, if it is male, then it is going to be 1, right? And what is the total number of possible outcomes? It is 2. So this is going to be 1 divided by 2, which is 0.5. So probability of a pupa to emerge as male is 0.5. And the probability for the pupa to emerge as female is also going to be 0.5, right? So this is how we calculate their probability in numbers. We give their probability values based on the previous information. But if we don't have a previous information, then we are going to give them equal chances of occurrence. And now we are going to discuss another concept in probability, and that concept is that sum of individual probabilities of all possible outcomes equals 1, right? So this is very important in discussing the probabilities. And we are going to take the example of coin. So we had 2 outcomes. The probability of head was 0.5 and the probability of tail was 0.5 as well. So when we take their sum, it is equal to 1. So probability of head plus probability of tail is 0.5 plus 0.5, and this is equal to 1. Similarly, when we take the example of dice, in this case, the probability of 1 to appear is 0.1667. Probability of 2 to appear in a single event of dice rolling is also 0.1667. For 3, it is also 0.1667. For 4, it is also 0.1667. For 5 as well, it is 0.1667. And for 6 as well, it is 0.1667. So these are the individual probabilities of all possible outcomes. And their sum should be equal to 1. So when we take their total probability, this is equal to 1. So this is an important concept. And then when we talk about the jelly beans, we took the example of jelly beans as well. So we had calculated the probabilities for all the colors. So probability of red is 0.2778, probability for yellow is 0.25, probability for blue is 0.0833, and probability of pink is 0.3889, and their sum is equal to 1. So total probability is equal to 1 of all these possible outcomes. And similarly, when we talk about the Dixella example that we took, so the pupa species, the probability of Dixella automalis is 0.8 and probability of Dixella attica is 0.2, and the sum of their probabilities is also equal to 1. And similarly, when we talk about the sex of the pupa, then probability of male is 0.5 and probability of female is 0.5. So their total probability is 1. Right? So the sum of the individual probabilities of all possible outcomes, it should be equal to 1. So this is another concept, and which is very important, that when you have calculated probabilities of all the individual outcomes, and when you take their sum, then the sum of their probabilities should be equal to 1. And if their sum is not equal to 1, it means that you have done something wrong in the calculations, right? So you take the individual probabilities, you calculate the individual probabilities of all possible outcomes, and then you take the sum of those individual probabilities, and that sum should be equal to 1, right? So this is an important concept in probability. And now there is another important concept related to probability, and that is probability distribution. So what is probability distribution? It is basically the breakdown which shows the individual probabilities of all possible outcomes and which adds up to 1. So when you show up, or when you represent the individual probabilities of all the possible outcomes into a single table, into a single distribution table, then that is known as the probability distribution. For example, here we have the table which represents the probability distribution of picking up of different jelly beans, and we have the individual probabilities of the 4 possible outcomes, which is red jelly beans, yellow jelly beans, blue jelly beans, and pink jelly beans. And we have written their individual probabilities. And when we take the sum of these individual probabilities, this is known as 1. So this breakdown, which shows the individual probabilities of all the possible outcomes, is known as the probability distribution, right? So today we have discussed the concept of probability, that what is meant by probability in statistics. It is basically just quantifying the chances of anything to occur, of a nominated outcome to occur from an event, right? And then we discussed that the probabilities, the sum of the individual probabilities, that should be equal to 1. And when we give the breakdown of all the individual probabilities of all the possible outcomes, so that distribution is known as the probability distribution, right?